let's say I have a horizontal pipe and at the left end of the pipe, let's say at the left end of the pipe, the area, the cross-sectional area, so I'll call that area 1. Let's say that is, I don't know, it's equal to 2 meters. Yeah, let's use simple numbers. 2 meters squared. And let's say it tapers off. It tapers off so that the area, the cross-sectional area at this end of the pipe, so area 2 is equal to, I don't know, half a meter, half a square meter. And let's say that, just the typical, we have some velocity at this point in the pipe, which is V1, and then the velocity exiting the pipe is V2. And let's say that the external pressure at this point, essentially being applied rightwards into the pipe, let's say that pressure 1 is, I don't know, let's say it's 10, let me write in a bold color, let's say it's 10,000 pascals. And let's say that the pressure at this end, so the pressure 2, and so that's the external pressure at that point in the pipe, let's say that that is equal to, I don't know, let's say it's equal to 6,000 pascals, right? And so given this information, let's say we have water in this pipe. There's just generally, so let's draw water. And we're assuming it's laminar flow, so there's no a friction within the pipe and there's no turbulence and all of that. So using that, what I want to do is I want to figure out what is the flow or the flux of the water in this pipe. So how much volume goes either into the pipe per second or out of the pipe per second. And we know that those are going to be the same numbers because of the equation of continuity. So we know that the flow, which is R, which is volume per amount of time, that is the same thing as the input velocity times the input area, right? So the input area is 2, so it's 2v1. And that also equals the output area times the output velocity, so it equals 1/2 v2. And then we could rewrite this that v1 is equal to 1/2 r, and that v2 is equal to 2r. So this immediately tells us that v2 is coming out at a faster rate, right? Just based on the size of the openings. And then we also know, because V2 is coming out at a faster rate, but we also know because we have much higher pressure at this end than at this end, that the water is flowing to the right. The pressure differential, the pressure gradient, is going to the right. So the water is going to spurt out of this end and it's coming in at this end. So let's use Bernoulli's equation to figure out what the flow through this pipe is. So Bernoulli's equation, let's just write it down. P1 plus rho GH1 plus 1/2 rho V1 squared is equal to P2 plus rho GH2 plus 1/2 rho V2 squared. Well, this pipe is level, right? The height at either end is the same. So these H1 is going to be equal to H2, so these two terms are going to be equal, so we can cross them out. We can subtract that value from both sides, and we're just left with P1. And what's P1? P1 is 10,000 pascals, so let's start substituting numbers. 10,000 pascals plus 1/2 rho times V1 squared. Well, what's V1? Well, that's R over 2. We figured that out up here. So V times R over 2 squared is equal to P2, well, that's 6,000 pascals, plus 1/2 rho times V2 squared. We figure out V2 is 2R. 2R squared. Let's just do some simplification. So let's subtract 6,000 from both sides, and we're left with 4,000 plus, let's see, we get R squared over 4, and then a 1/2. So we'd have rho R squared over this is over 4 over 1/2, so it's over 8, is equal to, we already subtracted the 6,000 from both sides. So we'll have 1/2 times r squared times 4. So this is 2 rho r squared. See, we could multiply both sides of this equation by 8 just to get rid of this in the denominator. So we'd get 32,000 plus rho r squared is equal to 16 rho r squared. And subtract rho r squared from both sides of this equation, we get 32,000 is equal to, well, this is 1 rho r squared. This is 16 rho r squared. So this is 15 rho r squared. And then what's rho? What's the density of water? Well, the density of water is 1,000 kilograms per meter cubed. So this is 1,000. So let's divide both sides by 15 times rho. So let me switch colors. So we get r squared is equal to 32,000 divided by 15 rho. Rho is 1,000, so r squared is equal to 32,000 over 15,000, which is the same thing as 32 over 15. So r is equal to the square root of 32 over 15. That's going to be meters cubed per second. And let's see. Let me get my calculator. Handy calculator. Did I actually remove my calculator? I think I did. Let's get my calculator going. So I get 32 divided by 15 is equal to 2.1, and then I take the square root of that, 1.46. So the answer is R is equal to 1.46 meters cubed per second. So that is how much, that's the volume of water that is either entering the system in any given second or exiting the system in any given second. And we can figure out the velocities too, right? What's the velocity exiting the system? Well, it's 2 times that. So it's like 2.8 meters per second exiting the system. And going in, it is half that. So it's like 0.8 meters per second. But anyway, hopefully that gives you, well, actually 0.7 meters per second. That gives you a bit of an intuition, more intuition on fluids. And that's all I'm going to do for today. I'll see you in the next video, and we're going to do some stuff on thermodynamics.